think we're live except the camera's not. Let me see if I can get it to come on here. Let's see. There we go. All right. Now we're good. Let's see. So we have been talking about frames and machines. We've done a couple of examples of frames and machines. We talked a little bit about how they're different from trusses, and so we can't use the same method of joints and method of sections. We talked about two force members because those can be crucial to working out one of these frames and machines. Normally on a frame and machine, what you're doing is trying to find what are the reactions at the various pins that are holding all of the frame components together. And we did say early on when we were talking about frames and machines that the difference, or a difference, between trusses and frames and machines is that in a truss, all the pieces, all the members are two force members or the zero force members, which they would still look like two force members, just the force would be zero. And the frames and machines have at least one piece, and maybe more, but at least one piece that it behaves like a beam. And also we said, like at the very beginning of the quarter, that the first third of the course is talking about axial forces, axial strain. There was some shear strain and shear force, shear components in there also, but things were stretching or maybe compressing. And now we're in the middle third of the course. Things can not just stretch or compress, but they can also bend, and we might say flex. And that's what this beam piece does. So at least one piece in a frame and machine acts like a beam. And so that's what we're going to look at. We're going to look at beams today. Maybe in the context of frames, we'll get to one later on, but let's start just isolated beam right now, so that we're not really talking about necessarily it's in a frame, but it could just be a single beam on its own. So let's talk about that for a second. All right, gotta reposition this thing. All right, let's just draw, for the sake of now, a rectangular beam. So this is the side view of a beam, and in a frame, usually the two ends, or at least some points, it may be more than two ends, but some points on the beam are going to be supported by pins. There could be some overhanging parts, and there's a couple of different ways we could support the beam itself. I'm going to draw this one in what's called a simply supported arrangement. And what that means is that there's a pin somewhere supporting the beam, and somewhere else there's a roller. So I'm going to put them at the ends. Let's see if I can straighten that line up. It's pretty crooked. I don't know why I was... Actually, I think I have a rectangular shape here that we can use. Make it much nicer. All right. Then we'll put a roller. We just show it as a wheel over here. So this is a simply supported beam, and this could be like two pins at either end, and that would still work as far as how it might fit into a frame or whatever. Here we're kind of looking at it on its own, and maybe it's a beam in a floor for a building or some sort of structure or something like that. It's just a beam. We're looking at the side of it, so this is a side. These beams have cross sections that a lot of times look like the letter I, so they're called I-beams. Maybe they have a C-shaped section, a channel, a right angle, so it looks like an L. So there's all these different types of beam cross sections, and we'll get to those. They'll be important once we start working on figuring out what happens to the beam. But for right now, let's just deal with the beam in general. So let's put a point load on here. Doesn't matter how much force. We just call it P. It could be anything. If this force is great enough, so large enough magnitude, and the beam is skinny enough, small enough, then we will deflect the beam. And so I'm going to exaggerate it, but the beam is going to do something like this. It's going to bend or flex. So it's flexing or bending, deflecting. All those words kind of are describing that the beam is no longer flat. It's curved somehow. So if you think about this, the fact that we're pushing down on the beam and it bends, and let's take and look at a really tiny piece of this beam but enlarge it. So that little piece would be curved. So this is a enlarged view of that little circled piece of the beam, and exaggerated on the amount of curvature. These beams typically do not curve and bend this much. It's very tiny amounts of deflection in most things that you would actually design a beam for, because you normally don't want a lot of deflection. So if we have some point on this beam, well, let's look at 3 points. Let's look here. Let's look in the middle. Let's look at the bottom. So originally, before we put the point load on here, this beam was horizontal. It was flat. And now I have pushed on it enough to where it curves. And if we look at the length of this line compared to the length of this line, they're very different. It's not an optical illusion. They're different lengths. So what has happened is the green. Oh, and let's compare them to the original, or the center. So this line is the original length. It's not stretched or compressed. So this is the original length. If I measured the length of that dotted blue line, it would be the original length of whatever section this was before it started bending. Oh, let me make sure I've got the chat open in case anybody post any questions. There we go. Now I can see it. All right. So the original length doesn't have any change in length. So there's no strain. Remember, strain depends on there being some sort of change in length, or at least axial strain does. The green line is shorter than the original length, which means that if it's shorter, it got shorter, that it has a negative strain here. And if you remember Hooke's law said that sigma, the axial stress, equaled E, modulus of elasticity, times epsilon, the axial strain. And so if it has a negative strain, then it also has a negative stress. So we are using compression to talk about negative stress. So there's compression on this top surface of the beam. And if we look at the bottom surface of the beam, the yellow line is longer than the original length. And same rationale, it has a positive strain, therefore it has a positive stress, and we talk about positive stresses as tension. So there, on this yellow line, the bottom of the beam, there are tensile stresses. So if you think about compression as negative, tension as positive, and I'm transitioning between the two of them, somewhere in there, there's zero. And if you think of the original length, this little dotted line here, it has original length, so that means it is the zero strain, which would be zero stress. So there's zero stress on this line. And what we're going to assume and is that I'm going to draw this as a compression because it's going to the left, so we'll say that means it's negative. Zero stress in this area where the beam has not changed length, it's the original length. Maximum compressive stress up here on the top of the beam. Maximum tensile stress on the bottom of the beam. And then there's going to be a linear line. Well, I kind of missed, didn't I? See if we can make those line up any better. There we go. And it's going to vary, as we get closer to that mid part of the beam where there's zero stress, the stress is going to decrease. So whether you're in compression, it's going to get more and more positive until it gets to zero. And then once it gets to the 0 point and you keep going deeper into the beam, towards the bottom of the beam in this case, it gets more and more positive until it gets to the maximum positive stress in the beam. And so beams that are bending have both compression, zero, or not both, have all compressive, so negative stress, zero stress, and a maximum positive stress, and then everything in between those two maximums throughout the cross section of the beam. So that's kind of the idea for a beam in bending and how it's different from a beam that's in tension like the two force members were. So the two force members, you were either just pulling on them or pushing on them, and if we drew this same kind of thing here, it would just be uniform across it. It would be all tension and all the same magnitude, or all compression and all the same magnitude. So it would just be kind of a rectangular stress distribution type shape versus these triangles that we have on this beam. And so that does mean the beams are going to behave differently from a two force member that might be in a truss or whatever. So let's do a couple of things to work on these beams. Let's make some room so that I can draw some new stuff. Move that there. Delete that. All right. Let's talk about the idea that where this zero stress occurs. So to do that, we need to look at the end of the beam. So now I need to scroll back up. This is the side view of the beam, and the end of the beam, it might be a rectangular beam, or it could be a T-shaped beam, or an I-shaped beam, or a C-shaped beam, or an L-shaped beam. All these different cross sections. So we do need to know something about this cross section. In order to know where this original length is. So let's just go with the rectangle because that's our simplest thing that we can do. So if our beam has a rectangular cross section, then this point where there's zero stress is located directly in the center. But it's not the center, it's that centroid. So whatever the centroid of the cross section, whether it's a T or an I or a rectangle or whatever, circle, doesn't matter. The centroid of that shape is where there's zero stress in the beam, with the original length. So there's no positive stress, no negative stress, zero stress. We call that point the neutral axis. And it's located at the centroid of the beam's cross section. So again, it doesn't matter what shape the beam is. You find the centroid of it. In this case, if it's a rectangle, then it's just, half of the height. But other cross sections could be more complicated. Maybe you need to look up the where the centroid is. There are tables and tables of beam charts where you have a name of a beam. We'll talk about that in a second. And you can go look up different properties, including where the centroid is. Or maybe it's a beam that you have fabricated yourself and you know all the dimensions of it. And so you know the dimensions of the cross section. And you can use the centroid approach that we did a few weeks ago, maybe last week, and figure out where the centroid is with kind of our bookkeeping method and find the location of a neutral axis that way. The important part about the neutral axis is it's where you measure from if you want to calculate some other stress in the beam, and it's the point where there is no stress. So it's kind of your reference point when you're talking about calculating the flexural stress in a beam. You measure that flexural stress from the neutral axis, either above it or below it or whichever. Let's talk about beam names, beam designations for a little bit so that we can maybe look at some charts and get some of this data. So your book, back, I don't remember what page, but in the back of your book, there are a series, maybe 5 or 6 different types of beams that give you some different data points. They give you the location of the neutral axis, the cross-sectional area of the beam, different dimensions of the beam, things like that. And they do that by naming the beams with a agreed upon convention. And so a beam name might look like W4 by 20. I don't know if this is an actual beam or not, but it follows the right rules. All right, so the letter, so the W in this case, what that does is it describes the cross-sectional shape, so like the general shape. So a W beam does not actually look like a W. W stands for a wide flanged I-beam. So the cross-section actually looks like the capital letter I, but W means wide flanged. The flanges on an I-beam are the top and bottom parts, the parts that kind of stick out, that make the top and bottom of the eye. So W would be a wide flanged I-beam. S, again, the beam does not actually look like the letter S. That's a standard flanged I-beam. So the cross section, if I were to draw the cross section of a W versus an S, W would look kind of like this, and the S would look, we'll move it over here, more like that. So the flanges are more narrow on the standard flange I-beam than the wide flanged I-beam. We have T. This is a T-beam. It really does look like a capital letter T. So it's got one flange on the top and a stem coming down. We have a C. So these are channel beams. So the T-beam cross-section looks like T. Channel beam looks like a blocky letter C. So it does look like a C, but it's kind of blocky, right? So it's half of an I-beam, more or less. I think we have L also in your book. And these are right angle. So they look like a right angle, like a capital letter L with a really long bottom part. There's a WT. This is a T-beam that has a wide flange across it. So this is a wide flange T-beam. I think those are all the ones that your book uses or has charts for. I think all of those. There might be another in there. You don't really need charts for rectangles and circles and stuff like that. But, well, you could, and there might be some because there's more information than just the shape in the chart. Your book does not have circles and rectangles. It has these. All right, so that's what the letter is telling you. It's telling you about the shape of the cross-section. The first number, get some more room, so the 4 in this case. This is the nominal, they call it depth. You might think of it as height, but the nominal depth of the beam. So in our case, if we have a W4, that means we have a wide flanged I-beam, something like that. And this distance from here to here, now this is nominal, so it's approximately 4 inches, assuming that these 4 by 20 is talking about a US sized beam. You do have similar charts that have the same beams, but they are given SI designation, so the 4 inches becomes whatever number of millimeters. I think they're in millimeters. Pretty sure they're in millimeters. We'll look at that in a second. All right, so that's pretty straightforward. It just gives you a rough idea. You have to go into the actual charts to figure out the exact depth, but it'll be close to 4 inches. Sometimes it'll be exactly 4, but a lot of times it'll just be 3.9 or 4.1, something like that. The second number, the X, is just, you read this as W4 by 20. It's how you read it. I guess I could spell out 20 since I spelled out 4. So that's how you would read W4 by 20. It's not W4x20 or times 20 or anything like that. So the X just means the word by. The second number is the unit weight of the beam. So you have to consult your chart to see what the units are. But if we're thinking of this 4 as being inches, then the 20 is going to be pounds per foot. So that would mean that if you had a 10-foot long beam, it weighs 200 pounds. And so that designation gives you a lot of information. It doesn't give you like detailed information in the charts. You've got all sorts of detailed information, but it gives you a pretty good idea of what this beam looks like. If we look up the actual beam chart, let's see if I can get one of those up real quick. Let's see, I think there's some in our reference folder that I have. Let's see, well, there's some in here. So these exam reference 1, exam reference 2, those have all the ones that are in your book, I believe, but it's really tiny. Let's look at, here's a W. So I don't know if W4 by 20 is going to be in here, but let's look and see. No, they have W4 by 13. So W4 by 20 is made up. All right, let's find a beam and look at all the stuff that's on here. Let's find one of the ones at the top so that we can zoom in and see the headings on it. So you could probably see this. Can we do one more? Well, it cuts off this other part over here, but I think we can do, there we go. All right, so let's just look at the top beam, W36 by 230, so that it's easy to see and track in our table here. So you have, this would be a 3-foot deep beam. So from bottom of the flange to the top of the flange is 3 feet, 36 inches, more or less. Not exactly 36, but more or less nominally 36. It weighs, if you cut off a 1 foot long section of this beam, it weighs 230 pounds, just that one section. So you can imagine this is a really, really big beam. We've got the cross-sectional area. So sometimes you need that. Maybe you're calculating the stress that needs the cross-sectional area number. It's not really practical. They give you a kind of a view of the cross-section. You can see it shapes like an I-beam. It's not really practical to go in and try to figure out if this, to calculate the cross-sectional area from dimensions. For one thing, these cross-sections are very idealized. A real I-beam is going to have the flanges be tapered towards the end. They're not going to be pure rectangles the whole time. So it's going to be hard to calculate this by measuring the beam. So you go in the charts and find the cross-sectional area. Here's the actual depth of the beam. So it's close to the 36 number, but it's 35.9 inches. So that's how the 36 is nominal. And then you go find the actual depth of it. We have flange width and thickness. So we do have some dimensions for the flange. So the flange width is going to be, how far is it across the top or the bottom, same flanges on top and bottom of the beam. And you have a rough idea of the thickness. So this is 1 1/4 inch thick flange. So it's gonna, maybe if I draw over on this page, let's do this. So let's name some things here. So there'll be a little bit more of this sort of shape to the flanges. Maybe not quite as dramatic as I drew it there, but something like that. So again, we have the depth. We have flange width is this one. We have flange thickness, and I've drawn it really tapered, so obviously this one is not the same thickness everywhere. And the flanges are, let's see, we'll do them red. So this is the flange, and then this is a mirror image of that same flange. So those are the flanges. This part here, for an I-beam, this is called the web. For a T-beam, the one that doesn't have two flanges, only has a flange on the top, that same piece is called the stem. All right, let's go back and look what we have. Here's the web thickness. So you have the web thickness, 3/4 of an inch. So that would be this. Then I have two sets of the same thing, ISR, but there's one set of IS and R under this thing called axis XX, and there's another set ISR under a column called axis YY. So what these are is there are two different ways you could install this beam, two really obvious different ways. You could put this beam in your building or whatever you're using, and you could put it in this way, or you could put it in this way. So you could do one of these two orientations. Most of the time, you're going to do, oh, hold on. Thought I clicked on the, there we go. Most of the time, you're going to do it where the XX axis is the one that is horizontal. But it is possible that you load it up where you have the YY axis. Now, these axes don't have to be horizontal. What it's actually talking about is where are these axes in relation to the loads applied to this beam. So most of the time, you apply the loads to the top of the beam, like we did way back up here. You know, if this was our I-beam, then the cross section looks like that, and we're loading perpendicular to what's labeled the XX axis. But you can have situations where there are significant loads on the what normally is considered kind of the side of the beam, and so that's why I have two sets of numbers for these I, S, and R values. We don't know what any of those are right now, but that's why I have two sets of them. It's because I could be loaded in two primary types of ways here on the beam. So what those numbers are, and we'll use two of these. We won't really use R, but I, you have what's called the moment of inertia. This talks about how stiff the beam is. S, we have section modulus. We'll use that when we're trying to pick out a beam from a list of possible candidate beams. Then you have R, radius of gyration. We won't really use that. There is most beams have some little description down at the bottom of this chart that describes how that designation is read. So this is a W means wide flanged I-beam, followed by the nominal depth in inches, so it tells you your units, and then the weight in pounds per foot. So you would have this kind of description so that you would know what these designations are referring to. And so we have that for a whole set of beams. In general, the biggest beams are at the top of these charts, and the smallest beams are at the bottom of this chart. Now there could be a line or two where they flip-flop, and it kind of depends on how you think of large and small. So different pieces of one beam might be like, it might have a really thick web but thinner flanges, or vice versa, and so it has a technically smaller weight, but it shows up in a different spot in the chart. But in general, smallest on the bottom, biggest on the top. All right. What we're going to do with these... Whoa, hit my printer. What we're going to do with these values, mostly, is look for the moment of inertia. We'll need that in a minute. Maybe it's this area sometimes. Sometimes we might look at the dimensions here. The depth we'll look at occasionally also. We'll need that. Let's look at a different chart, because the I-beam doesn't have one thing in there that maybe the WT will have. So the WT has a new column right here, Y sub C, and it has a a new label on its picture diagram labeled Y sub C. This is the Y coordinate of the centroid. So the I-beam, they don't bother to give you the centroid because you can, by observation, tell that it's symmetric about the XX axis and the YY axis. And so there's no reason to tell you that the centroid's right in the center of this one. On the WT, you know that the centroid is somewhere in here, but you need an exact number. And so they give you that. Now, it is measured from the top of the beam. I think most of the examples that I did and most of the web work and homework exam problems reference the bottom of the beam. So do make sure that you look at this diagram to see that, oh, they're measuring the distance from the top of the beam down to the centroid. And that's where they put the XX axis, or the neutral axis. All right. What can we do with this? So what we can do is we can calculate flexural stress in the beam. So flexural stress, or bending stress, so it's kind of the same thing. The equation for this, it is going to be, if we look at our diagram here, all these arrows I drew, they look kind of like the normal stress arrows. They're perpendicular to the cross section. The cross section, this is the side view that I'm looking at right here. The cross section is this rectangle, or the T, or the I, or whatever. They're perpendicular to that cross section, so they're kind of like an axial stress, except that they vary. They're not averaged across there. There's positive and negative, so it's not the same. That's why we call it flexural stress or bending stress. But it is going to use sigma because it is an axial type of stress. The stress is perpendicular, or normal stress. Maybe that'd be better. It's normal to the cross section. The equation, we're not going to derive this equation. I'm going to just give you this equation. We might go back and derive it later if we have time to make sense to put that in. Right now, I'm just going to give it to you. Negative m times y over I. So remember, axial stress or normal stress was force divided by area. This is similar format. M is not a force. M is the internal, so it is an internal deal, not an external applied load. Internal bending moment so we'll have to describe and figure out how we're going to calculate this internal bending moment. It's going to be the same idea as when we found the internal force, the internal normal force or axial force. We're going to draw a free body diagram, cut a beam open, draw a free body diagram, and figure out the bending moment. But it is a moment. It's not an axial force. Y is the distance from, remember I said we were going to use the neutral axis as a reference point. So distance from the neutral axis to the point of interest. So let me talk about that a little bit. Back up here, the neutral axis is right in the center. It's on this dotted blue line. And the stress varies from that point at being 0 to maximum compression on one side of the beam and maximum tension on the opposite side of the beam. And it varies linearly between those. So I have to pick where do I want to calculate the stress. Where on this cross section do I want to know the stress? Typically, I want to know either the very top of the beam or the very bottom of the beam because that's where the maximum compression and tension are. But I could actually calculate the stress at any point, and if I put 0 in there, then the sigma equation spits out a 0 because I have m times 0 divided by I, so that's just 0. And so it does predict the 0 stress at the neutral axis. If I'm measuring from the neutral axis 0 inches, then there's 0 stress there. 0 bending stress. There are other stresses that we're not thinking about right now. I also mentioned very early in the quarter that even though we're dividing the course into 3 axial, flexural, and torsion sections, we're not combining all of those. But you could have a beam that is twisting, bending, and stretching all at the same time. So the next course after this will begin to put all 3 together at the same time. Here, we're not going to do that. All right. I is called the moment of inertia. Second moment of area is another thing it could be called. So remember, the first moment of area was the numerator in our centroid equation. Second moment of area is similar, except instead of a first, it's a second, so integral of y squared dA instead of integral of y dA. So you might see it called second moment of area at some point. This moment of inertia is a cross-sectional property, so it's not the area like in our normal stress equation, force divided by area, but it is talking about the cross-sectional area. And so the bigger this number is, it's in the denominator, so the bigger it is, the smaller the stress will become. So it's kind of describing how rigid and how difficult to bend the beam this particular cross-section is. And it is one of the numbers in our chart. Right here's moment of inertia, and here's the other one, depending on if you're loaded this beam perpendicular to the XX axis, which is normal, or if you've turned the beam on the side or loaded the beam on its side perpendicular to the YY axis. And look at the difference in the values here. When you load the beam perpendicular to the XX axis, as usually intended, this moment of inertia is 15,000, has inches to the fourth are the units on it. But when you load it from the side, it's 940. So you could take the same kind of equation here, and if the denominator is 15,000 in one case and 940 in the other case, then you can imagine the difference in the stress under those two different loading scenarios. So it does make a difference which orientation you load an I-beam or a T-beam or even a channel beam, those sort of things. A square beam and a tube, those are the same either direction, so that's different. But the shapes of I-beams and T-beams are optimized for particular types of loads. All right, let's try and use a named beam so that we don't have to calculate the moment of inertia. That is a thing. You calculate it similar to how you would calculate a centroid, and so we'll do that probably either later this week or next week. I'm not sure when it's on the schedule. We'll do it soon. But for now, we have charts that tell us moments of inertia. So let's just use a chart for now. Let's use a smaller beam, though. These big giant beams are, they're too big. Let's do something in this range. W10 by 22. Well, let's use that. So let's create a problem where we have a W10 by 22. And let's put some load configuration on it. Here's our simply supported beam. So we'll put a pin in a roller. Let's put a, oh wait, I even have arrows here. Let's do that. Put a point load. Let's put a distributed load because we haven't done a whole lot with distributed loads. So let's, oh, I guess I have to do this every time. Wish it would kind of hold that for me. These are all a little crooked, but that's okay. They're all supposed to be straight up and down. All right. So we've got a point load and a distributed load. We need some dimensions on there too, though. So let's say we've got this dimension. Oh, I didn't want to move it. We need something here. Sure, land on that one. Oops. Let's just, we got a grid here, so let's just use those as our 1, 2, 3, 4, 5, 6, 7. We'll call this 7 feet. 1, 2, 3, 4, 5. We'll call this 5 feet. We'll call this 250 pounds. And let's call this 100 pounds per foot. And we've got this beam as a W10 by 22. Let's assume, I didn't quite get it there, but let's assume that I've got the triangle and the circle lined up perfectly on the ends of the beam. I don't know if I can, yeah, I don't know if it's easy to move that now. More like that and like that, so that the reactions are right at the end of the beams. Normally we just ignore the very end of the beam and assume that the pins and rollers are, they're flush with the end, so the reaction can be there. Sometimes you will have where it's obviously not, like maybe like this, where there's a little piece of the beam that's hanging out. We call that a cantilever, and let's not get into that just yet. All right. So the first thing that I need to do is actually get rid of the pin and roller. I need a free body diagram because I need to know the reactions that the pin and the roller are imparting on our beam. So let's actually delete that and delete that and replace them with the pin would have a horizontal force, potentially, well, vertical and potentially a horizontal force, and then the roller is going to have a vertical force. And we'll call those, we'll just call the left-hand side point A. So this will be AY, this will be AX, and this will be point B. We'll call it BY. They weren't actually labeled on the original beam, but we'll just call them that. All right. Now I have these three unknown reactions. Technically, I can just look at it and see that AX is 0 because there are no other forces that are angled or pushing in the X direction. So that one's just 0. So I just really need to find values for AY and BY. What I normally do is do summation of moments, and I normally do the summation of moments about wherever the pin is. There's going to be a pin and a roller in a simply supported beam. So I'm going to do moments about A. I'll do clockwise as positive, and those have to be 0, and that means that this beam is not rotating about point A, which I know it's not doing if it's in equilibrium. And that does not mean it's not bending, but it's not spinning around point A. It could be bending. That's what we're looking at later. All right, so I've got 250 pounds times, oh, I've kind of did my units. I didn't even notice that. I left off one. Let's add it in real quick. Not my units, but my dimensions. Put that one in there. And that one's 2 feet. Okay. So that 7 should have actually gone only to that first mark. Right there. Kind of weird as arrangement of units, but that's what we ended up with. All right. So it's 250 pounds times 7 feet. That's the moment that the 250 pound point load creates about point A. We've got this distributed load. It is 100 pounds per foot, and it is 5 feet long. So if I were to take and concentrate that into a single point load, that would be 500 pounds. And it would be 2.5 feet from that point anyway. So it would also go around clockwise around point A. So I'm going to give that a plus in my equation. 500 pounds times that distance is 7, 8, 9, 10, 11 and a half feet. And then I've got BY, so that part takes care of the distributed load. BY is the way I drew it, going counterclockwise around point A. It would make the beam rotate counterclockwise about point A. So minus BY, and it has a moment arm of 14 feet, 7 plus 2 plus 5. Well, let's do it the same as I did all the others. These all have to add to 0, or else the beam is somehow spinning around point A, which I know it shouldn't be doing. So therefore, we should be able to solve for BY. So I got to get my calculator out. And we've got 250 times 7 plus 500 times 11.5. Move BY to the other side, it becomes positive. Divide by 14. 535.7 pounds. Then, depending on how confident I am, I could either do summation of forces in the y direction and get BY. That's what I'm going to do. Or I could do summation of moments about B, get a value for AY with a similar equation, and then check that they do both solve together to equal 0. Not that they equal 0, but they equal actually 750 pounds. If I did summation of forces in y direction, they made a true equation. I'm just going to do summation of forces now. But you could do moments about B, get a value for AY, then do forces in the y direction and see if it gives you 0 equals 0. So I've got AY minus 250 minus the total 500 plus by equals 0. I just found a value for by that I can plug in. So therefore I get ay equals, let's see, 214.2, well, 0.3 pounds. So this part is nothing new. We've done this already. So this is just how you get started. You have to know, most of the time, you have to know the external reactions. There are some cases where you don't have to, particularly with the cantilever beams, but most of the time you're going to need at least one set, the pin or the roller, of external reactions solved before you can do anything else with the beam. All right, we're trying to solve this equation, sigma equals my over I. We don't have any of that information. We could look up I, so let's do that. So W10 by 22 we haven't specifically said which way we've loaded this beam. So let's go to our diagram here and point out that this is the way the cross section is oriented. So this means all the loading is perpendicular to the XX axis, like this. So we're going to use the XX column for finding the moment of inertia. So we said this was a W10 by 22, and we want the moment of inertia under the XX set of values. So this is 118 inches to the fourth, and just checking that we're on moment of inertia and XX column. So 118 inches to the fourth. So as long as you have a beam with a designation, you should be able to just look up the moment of inertia without having to calculate anything. Do be careful that there are two sets of beam data. There's the US set of data and the SI set of data, the metric set. And so you got to be on the right table. It won't really work. Like none of the beams that I can think of are named the same across the two different tables, so you couldn't actually look up the wrong thing. It'll just look like the beam doesn't exist. So make sure you're on the right table. All right, so we have I. So we have the denominator. We need M and Y. So let's do Y next. That's the next easiest thing. So we described Y as being the distance between the neutral axis of the beam and the point of interest. So let's draw our cross section. Kind of like this. Okay, and let's get our depth. So we know it's close to 10 inches, but let's see what it actually is. So the W10 by 22, the actual depth is 10.17 inches. 10.17. We also know that since it's a I-beam, the neutral axis is just in the center of it, so 10.17 divided by 2. 5.085. I don't know if I'll have a room to write it there. We'll just put it over here. Okay. So the point of interest, my problem statement didn't say anything about the point of interest, but normally you want to find the maximum stress. And in this case, I is the same for any point. We're assuming that this beam does not change its cross-sectional shape from one end to the other, which is true for most beams. Most beams, if they start out a W10 by 22 on one end, then all through the length until you get to the other end of the beam, it's still a W10 by 22. I guess you could have some beams that are not that way, but typically that's going to be true. So that doesn't change. M does change from point to point on the beam, but it is not really going to show up on our cross section. So Y is the distance between the neutral axis, if the neutral axis is your reference, and the point of interest. In this case, let's just say the point of interest is the bottom of the beam, because that's where the tension is going to be. If we look at this beam, we don't know exactly what it's going to look like, but we do know it's going to, bend down somehow. And so the bottom's going to be in tension, and we want to calculate that tensile stress. So in that case, I would take this diagram, measure from the neutral axis down to the bottom of the beam, and that's Y that's going to go in this equation. So Y equals a negative, because I measured from my reference downwards, so it's a negative 5.085 inches. And so that negative sign, when we put it into our equation for flexural stress, it'll cancel, or it will interact with the negative sign in the equation itself to create a positive number, which tells us that the stress on the bottom of the beam is tension, which is what we expect for this beam. Assuming that M is going to be a positive number. So we do have to make sure of that. I guess we have no choice now except to figure out what M is. So M, like we mentioned, the name of it is the bending moment. And what it is it's the internal bending moment. And it is the force, or not force, but is the moment inside the beam that's actually causing it to bend. So if I look at this picture here, remember this is a free body diagram, as if we cut a little tiny section of our beam and blew it up. So where we cut it, we didn't draw any forces on these surfaces. We just kind of drew it and passed on from there because we weren't talking about them at the time. But there are forces acting and moments acting on those surfaces since I cut it away from the beam, and I'm looking at a little tiny free body diagram. There are bending moments and shear forces on these surfaces. So why don't we take this picture and work on it some more down here. All right. We don't really need this arrow. That was just pointing out that that was the neutral axis. All right. So the beam is having two things happen to it. Actually, there's a third thing that we're going to ignore. I'll mention it, I guess, in a minute, but two things that we're looking at mainly. And that is that the beam is trying to shear. So it could be that I load this beam up with the point load, and it doesn't bend, or at least it doesn't fail by bending, but it actually shears. So the shear failure would look like this. You know, that would be the shear failure. So it does something like that. It just shears it off like you cut with a knife or some scissors or something. Typically, if this is going to happen, it's going to happen really close to a support, because the beam would is much easier to just bend. You know, if you think about a ruler or something, it's easier to bend that than it is to shear it. So shear failure is not as common. You have to check for it, but it's usually not the actual mode of failure for one of these beams, unless you've got a heavy point load near a support where the beam can't bend. You know, the support is holding it in place. It can't bend and move around, and you've got this really heavy point load on it. Then yes, that could cause a shear failure. So we do have to think about it, but it's typically not the mode of failure, but it does exist. All right, so I'm going to erase this because I don't want to. We weren't really talking about that at that. Actually, let's just move it down to where we're down here. Let's see if we can. Come on. Kind of hard for it to move. Or we'll just put that over here just as a reminder. Shear failure. All right. So the shear forces are on these surfaces that we cut. So there would be a shear force here and a shear force over here. Let me check something really quick. I gotta check to make sure I've got these arrows the correct orientation. Let me see. Did I draw them the right way? Sheared, yeah, I did draw them the right way. It doesn't matter terribly much which direction, as far as the part failing. It doesn't matter which way you draw the shear, because it's going to shear one direction or the other with the equal strength, I guess, shear strength. But for later on, when we're deriving some other things that we'll do later with shear and bending diagrams, then these arrows matter for their direction. All right, so those shear forces, this could be the shear force on the right-hand side, and this could be the shear force on the left-hand side. That's all we need to know about them right now. I don't want to put this up here. Let me put this down at the bottom of it. I want something else up there. So those are the forces that could potentially be causing our shear failure. And it's straightforward. There's a shear strength for the metal. There's the cross-sectional area of the beam. You know, this W10 by 22 is 6.49 square inches. And you can just divide that shear force by that area, and you get the shear stress and compare it to the shear strength of the beam. So it's really straightforward. I'd mentioned that there is another stress that we're not really looking at. And it's also a shear stress. What happens, or what can happen also, is delamination. Now, this is not really an issue very often with a steel beam, but maybe a composite beam or some other type of beam. This could be an issue, and it could be an issue with some types of steel beams. But if you think about taking a book, like the phone book, something big, thick book or whatever, and it's got a soft cover on it, and you bend the book into a shape like this, all of those pages, in order for the book to bend, all those pages have to slide past one another. And in a beam, they can't do that. They're not individual pages, but they still want to do that. All the different layers still want to do that. And so a shear stress does exist between those, layers of the pages of the book. And it could be, particularly in some kind of composite or laminate type thing, that there's enough stress between those layers to delaminate the part. It doesn't happen too often. We're not even going to worry about calculating it, but it is a thing, and it is possible that it would happen. But we're not going to talk about it. So we still haven't got to M, though. M is what we want, the bending moment. So the other thing, if I look at this free body diagram, it would have, there'd be a force P applied to this thing to make it bend. And the shear force that I've got here would actually make them spin, so there's not going to stop them from spinning. Here is the moment on the right-hand side of our free body diagram. Here is the moment on the left-hand side of the diagram. And so these ML, and MR, those are the internal bending moments. They're the thing that go into our flexural stress equation right here, M. The way that I've drawn these arrows, those are the positive directions. So if you're looking at the left-hand side of a beam, normally when you cut a beam open to find the internal bending moment, you only look at one side or the other. This one, I've taken a little chunk out and looked at both sides. So that's why I've got both ML and MR on here. Normally you only have one or the other. And so if you're looking at the right-hand side of a free body diagram, then you need to draw the arrow counterclockwise. If you're looking at the left-hand side, ML over here, you need to draw the arrow clockwise. Those are the positive orientations for what we're going to do with beams from here on. Most of the time I'd tell you can choose whatever orientation you want, as far as left being right, left being positive or negative, up being positive or negative. You know, you can choose all of that. This one thing we have to agree upon so that our stresses end up the same. Otherwise, if you happen to assign a positive stress where I've assigned or positive bending moment where I've assigned a negative bending moment, or vice versa, then we won't get the same We'll get the same magnitude, but not the same value. You know, one of us will be positive, one will be negative, and so it creates confusion. So when we're dealing with internal bending moments, these are the positive orientations depending on what free body diagram you're drawing. All right, and I wrote them as ML and MR because they're not necessarily the same value. From one end of the beam to the other end of the beam can have different bending moments, internal bending moments. So in our beam, we have to decide where is it from, here's our x-axis, where is it from x equals 0 to x equals 14 feet that we're interested in finding the stress. We've decided based on the cross section that we wanted to know the stress on the bottom of the beam. We did decide that right here when we assigned y to equal -5 inches. That told us that we were interested in the bottom of the beam. But where along the length of the beam are we interested? Here, eventually we will, maybe we'll get to it next time. I'm not certain we will, but it's possible. We will be able to figure out where the worst case is and just calculate that point. We don't have enough information to be able to do that yet, so we don't know how to do that. So what we're going to do instead is I'm just going to pick a point. And I want to say that the point is right here. So we can pick any point we want. We'll just pick that one. And we'll say that that's 8 feet from the left end of the beam. And you'll have problems on exam 1 like this, where there's a beam drawn out and I specify some point on the beam, and that's the point where you want to find this stress. And so what that does is it tells you, okay, cut the beam open at that point, 8 feet from the left end, draw the free body diagram, and figure out what the internal bending moment is. So let's do that. Down here. So we'll do it like that. We had a point load AY. We had a point load P. We had a shear force on here. And we had a, now we have to draw this arrow the right way. So we're looking at the right side of a free body diagram. So I've got to draw this arrow counterclockwise. So there's M, there's V, the shear force on this surface. I forgot these other values. Let's see. 250 pounds for the point load. And AY is 214.1.3. And then we have some dimensions. This was 7 feet to the point load. I'm pretty sure that's what we ended up with, even though I kind of made it weird, but that's what we did. And so that makes this 1 foot because I specifically said that we're going to cut the beam 8 feet from the left end. So, you know, this is our cut surface over here for our free body diagram. So now I've got something that looks like any other frame free body diagram. Now I've cut it open, but it's got 2 unknowns. There's some things I know. It's got dimensions on it. I can solve for V and M here. I don't need to solve for V, but it's easy enough to solve for that we're going to do it just to make sure we can. So if I did the summation of forces in the y direction for this free body diagram, they have to equal 0 or else this piece of the beam is moving up or down, and I know it's not doing that. So 214.3 pounds minus 250 pounds minus V, the way I drew V, equals 0. Therefore, V equals, my calculator out, 250 minus 214.3. It's a negative, so it needs to be pointing up. 35.7 pounds. So really it's supposed to be pointing upwards, but that's okay. Again, shear doesn't really matter which way it shears. So we've got that value. It doesn't help us in solving our bending stress equation, but it would give us a value to solve for our shear stress. But if you remember, we looked at the area, and it was like 6.49 inches. Square inches. So therefore, tau is a really tiny number. 35.7 pounds over 6.49 inches squared. I'm going to drop the negative sign off since it doesn't matter. It's just a shear stress. 35.7 divided by 6.49, 5.5 psi. So essentially nothing. So, and that's typically what's going to happen, is that these shear forces are small compared to the beam itself, and so they're not usually going to be the mode of failure. All right, let's get on to finding the bending moment. So the forces in Y didn't solve it. The forces in X definitely won't solve it. Remember, concentrated moments. Maybe this is the first concentrated moment we've seen. We might need to talk about that. This curved arrow is a concentrated moment. So it's sort of like the concentrated load when you have a distributed load. But normally how we create a moment is a force times a distance. Some other thing somewhere has caused the same effect as a moment here, but there's not necessarily a force. Now, in this case, there are forces times distances. You know, they've got 250 pounds. I've got the 214 pounds. So they are working together to create this bending moment, this internal bending moment. But when we draw it as a curved arrow, it's a concentrated moment, in this case, a bending moment. And when I write a moment equation, it just is in the equation as a plus or a minus. So let's write the summation of moments about the cut surface here, so the 8 foot from the left end point. I'm going to say that clockwise moments are positive, although you might want to use counterclockwise positive because my moment that I drew is counterclockwise, but we can do whatever. About the cut, the shear force is on that cut surface, so I don't need to enter it into the moment equation about the cut surface. I do have a counterclockwise, so a negative 250 pounds at 1 foot moment arm. I have a clockwise, so positive 214.3 pounds with a 8 foot moment arm. And then I've got M. And M is already a concentrated moment. It doesn't matter that it's on the surface or about the surface that I'm looking for. It's just either plus or minus. And so I said in my equation, I said clockwise is positive. This arrow is drawn counterclockwise, so minus M. Those have to add to 0, or else this little piece of my beam is spinning about this cut surface, which again, I know is not true. It's not the same as deflecting or bending, flexing, all of those things. That's not spinning and rotating. So that's a different thing. Yes, it probably is moving around a little bit because it's deflecting and bending, but it's not spinning about the cut. So we can solve for M. And let's see. We get, well, 250 times 1 is 250. 214.3 times 8. And that would be, if I move all these things around, move M to the other side of the equal sign, it becomes positive. this term here would be positive, and I get M is 1464.4 foot-pounds, or I wrote them as pound-foot. Notice when I have M in my equation for the moment calculation, I don't do M times anything. M is, it already has units of foot-pounds or inch-pounds or Newton-meters, so it already has the distance in it. Whereas all these others, I did a force times a distance to create a moment. The concentrated moments are a moment. They don't need to be multiplied by anything to make them into a moment. So don't do M times 8 or M times 0 or anything. It's just M, either plus or minus. So this moment is what will go in this equation. It came out positive, which means this arrow is drawn correctly, which means that it matches the positive orientation for a internal bending moment drawn on the right side of a free body diagram. So all of that means is that this is a positive moment. And we just have to agree on what a positive internal moment is and what a negative internal moment is. And how we're going to do that is through drawing them the way they're shown on this diagram, where if you're drawing the right-hand side of a free body diagram, the moment is counterclockwise. If you're drawing the left-hand side, it's clockwise. What this does is, before we calculate our bending stress, I want to show this. We have a beam in bending with a M equals some greater than 0. I guess I could do M greater than 0, couldn't I? So it's positive, in other words. Puts tension on the bottom of the beam and compression on the top of the beam. But you could imagine a scenario where you're pushing up on the beam and you have tension on the top and compression on the bottom. That would be M is less than 0. If M is 0, it's just flat. It's not bending at all. There's no internal bending moment if M is 0. So the easy way to remember this is to think of positive moments, greater than 0. Negative moments, less than 0. So positive moment does this, negative moment this, and if you add a couple little I's, it's really easy to remember what the positive internal bending moment does and what the negative internal bending moment does to the beam. All right, so they told me that in 1993, I think, and I have never forgotten it. I don't think you'll forget it either. All right, let's calculate our stress. So we've got all the stuff to put into this equation to calculate the flexural stress 8 feet from the left end of the beam on the bottom of the beam's cross section. So if we're looking at this diagram, we're calculating the stress right here. That's what we're calculating. All right, so sigma equals, this negative sign here is part of the equation, so we're putting that in. I will try to remember to put those in. A lot of times I forget and I just assign the correct positive or negative for tension or compression, but I will try to remember to put it in there. M times Y over I. All right, so equals negative M, 1464.4 foot-pounds. And sometimes M is negative, meaning that the beam is bending with tension on the top of the beam. And so you could have negative, negative to make it positive. These foot-pounds, I want my stress to be in units of PSI or KSI, anything per square inch. So I want to get rid of the feet here. And there are 12 inches per foot. That will get me into inch-pounds. Y was, we measured that quite a while ago. Right here, negative, because we measured from the neutral axis which is in the middle of the beam at the centroid, to the bottom, so that's a negative y, negative 5.085, already in inches. We looked up in the chart, I wrote it down here, 118 inches to the fourth. Okay, now our units should come out to be pounds per square inch. Let's see what our number is. 1464.4 times 12 times negative 5.085, but I have that other negative so that it becomes positive, divided by 118. 757.3 psi. So 0.76 ksi. If you remember, the tensile strength of a steel is like 30, 36, 33, 32. You know, it's a 30,000 psi, somewhere in that range. And we're at 800 psi. So we're nowhere near at this point in the beam. So at this point right here, we are nowhere near any kind of failure from flexural stress. That's not to say that there aren't other points in the beam, you know, because we picked this one spot. If we picked a different spot, you know, look at our picture here. If I had picked a spot that was 9 feet, then this 1 becomes a 2, and the m over here, where's it? This value would change. This value would change, and so I'd have a different moment, a different internal bending moment. So this type of approach is good when you are given a very specific location. Find the bending stress, find the flexural stress in this beam given at a point 8 feet from the left end. You know, and so you're given a very specific location. Then you can go in, cut the beam open at that location, find what that internal bending moment equals, and carry on with the rest of your calculations. If the problem is saying something like find the maximum flexural stress in this beam, we need a different approach. So we need to know where is the maximum bending moment. Basically, if our equation, where did our equation go? There it is. We need to find the maximum value for m if we want to find the maximum value for sigma. So that's going to be a different thing. I think we will be able to do that tomorrow by drawing pictures of the shear and the bending anywhere in the beam. So we can follow a couple of rules and draw an actual picture that represents the shear force anywhere in the length of the beam and the bending moment anywhere in the length of the beam. And I think I don't want to start that today. We'll start that tomorrow. I'm going to open up the homework that goes along with this beam introduction. I haven't gotten many questions about frames, just a few, but if you do have questions about frames, let's not get too far behind on working on those frames before you ask me a question about them, because they are probably the harder part for exam 2 is frames machines. You've got some homework you can do. You've got the challenging problems, the optional problems, the required problems, all in web work, and just make sure that you're keeping up on that and not getting behind on getting too many things going at once. Frames and now beams, and then we'll move on to shear and bending diagrams, and so we'll keep adding stuff. All right. I will see y'all tomorrow at noon, and this is going to be tomorrow. Yeah, we're Thursday. Yeah. So tomorrow, and we'll do a little bit more of this, and we'll talk about how to draw those shear and bending diagrams. All right. I will see y'all then.